As we said before, this is our BV or Butler-Volmer equation. Of course, this is for the simplified situation that we assume no transport limitation. No transport limitation, which is you either actively stir the solution of a gas phase, provide the high gas flow to blow it, or you keep the current density to be relatively low so that the species concentration at the surface is the same as in the bulk. But anyway, this is the Butler-Volmer equation. It relates either O potential and the J, the net current density through for the electrochemical half cell reaction, and J0, as we said, would be exchange current density. Beta would be so-called symmetry factor. It tells the shape for the polarization curve from anodic versus cathodic. N would be the number of electrons transferred through the half cell or redox reaction, and F Faraday constant, R gas constant, T for absolute temperature. So this is Butler-Volmer equation. Let's look at what happens when we use this equation under condition that is, read to yourself, near equilibrium, which is very close to equilibrium. Or the current would be very low and the overpotential would be very, very small. So when we are near equilibrium, it essentially means the actual potential would be very, very close to equilibrium potential. We said overpotential is a potential difference between the actual potential for the redox or half cell reaction versus the equilibrium potential for the redox or half cell reaction. And when this difference or overpotential is very small, how small? We say the absolute value is less than 10 millivolts, then the exponents in the Butler-Volmer equation are very small, which is this term and this term within the exponent would be very small. How small? Let's give an example. For simplicity, assume beta, the symmetry factor, to be 0.5, and also assume one electron transfer and at ambient temperature, 25 degrees C or 298.15 Kelvin. If we plug these numbers in, the exponents, okay, because the beta is 0.5, the two exponents would be the same, and if we plug the number 0.5 times 1 times Faraday constant 96,485 coulomb per mole times, if we use this value, eta over potential absolute value of 10 millivolt or 0.01 volt divided by RT, 8.312 joule per mole per Kelvin, divided by temperature, 298.15 Kelvin. Then we would have this exponent to be 0.195. 0.195. Okay, remember what you learned in calculus. The e to the power of x would be approximated by 1 plus x when the x goes towards 0. And when, for this case, if the exponent is 0.195, e to the power of 0.195, you punch that into calculator, we will get a number of 1.215, which is approximately 1 plus this exponent number. The difference is around 2%, which is reasonable, Okay, so under this condition, we can have this simplification. The e to the power of x can be approximated by 1 plus x when x going towards 0, and in this case, at 25 degrees C, 10 millivolt of over potential, 1 electron, symmetry factor 0.5, this number can be applied. So then we would be able to simplify the Butler-Volmer equation. Okay, J, the net current density, would be J0 exchange current density times, within this big bracket, the first exponential term would be 1 plus exponent, okay, write it here, minus the second term of exponential term would be 1, because we have negative sign, 1 minus this term, okay, and then this plus 1 and this minus 1 would cancel out, minus minus become positive, so we would have J0 times one term we keep, minus minus become positive, okay, this is the second term. And then when you look at these things within the square bracket, minus beta NF eta plus beta NF eta. So this term and that term would cancel out. We would end up with J0 just times NF eta divided by RT. So again, this is for the simplification when we are near equilibrium, when the overpotential, in this case, smaller than 10 millivolt. And we evaluate even for 10 millivolt, 298.15 Kelvin, the numbers, this approximation is reasonable. Okay, so in this case, we linked J, the net current density, with eta, the overpotential, with a simplified relationship. J equals J0 times NF over RT times eta. We have a simple linear relationship between net current density and eta, which is overpotential for the half cell reaction or for the electrode reaction. Eta, remember, is a difference between actual potential for the half cell reaction versus the equilibrium potential for that half cell reaction. And this applies again under very small bias near equilibrium. The overpotential is smaller than 10 millivolt absolute value. Okay? And then under such condition, if we are near equilibrium, sometimes people define another term called charge transfer resistance. Charge transfer resistance. It's a resistance, so R for resistance, CT for charge transfer, it would be resistance would be overpotential divided by current density, eta divided by the net current density. And from this equation, eta divided by J, we would have RT divided by NF divided by J0. So this gives us the so-called charge transfer resistance. And you get that number through the polarization of overpotential current density curve when you are very close to equilibrium. When your overpotential is smaller than 10 millivolts, you get a linear relationship, and this charge transfer resistance, as you see, would be a constant because all these terms R, T, N, F are all constant, and J0, as we said, for a given system with a given microstructure is also constant. So this charge transfer resistance would also be a constant. Okay, and this give us a way to determine, in fact, experimentally measure the exchange current density value if we have a series of data points of measured overpotential versus net current. And of course, the measured overpotential has to be very, very small, smaller than 10 millivolt in absolute value. And then we can have a way to back calculate the exchange current density value, which is J0, using this equation.